Good evening, everyone. So today we'll be discussing the last chapter for this subject, that is flotation. So before starting, I will wait for a few minutes more for people to join for the class. Okay, so we can start today's class. Okay, so today we will be discussing flotation process. So flotation is a very effective process for separating the particles, mixture of particles based upon their surface property. So till now, previous classes, we have discussed that how the density of the material or the size of the material, based upon that we have sorted out particles into different categories, right? Or we have finally separated out the particles based upon those other properties. So today in this class we will be focusing on the surface property of the particle, and we will also be focusing on the ways or the methods to adapt to to modify the surface property of the particle, and so that we can extract or separate that particular particle from the mixture of other particles. So let's start. So as I already discussed, that flotation process is a surface phenomena oriented process which exploits the hydrophilic and hydrophobic nature of the particle. So these two varieties are there. Based upon that, the flotation separation efficiency uh, depends, and which can be summarized as a physiochemical surface property of the particles. Now, this process of flotation, it doesn't depend on the density or size of the particles in the mixture of particles. It doesn't depend on the size and density. It is mainly oriented with the surface phenomena property. So this flotation is widely used and also considered to be cost-effective separation technique for various applications other than mineral beneficiation, that is wastewater treatment, micro-oxygenation of beverages like wine, any kind of fermentation process, ink removal process, plastic recycling process. So these are some flotation application where we use this property, surface property of the particles, to separate out one desired particle from mixture of particles. Now this flotation, if you um, if you are experienced with some coal beneficiation plant, then you will know that for the coal beneficiation, froth flotation process is a very important step. So we will discuss that how the froth flotation occurs and what are the chemicals we need to add to modify the surface property of the particles for effective flotation process. So in this technique, the components like very fine particles, oil droplets or contaminants, they are separated from the mixture which is based on their hydrophobic or hydrophilic surface properties. The essence of flotation process depends on using the gas bubbles that you are introducing into the system, which will be used to capture the particles based on their surface hydrophobicity or hydrophilicity. So during a flotation process, hydrophobic या hydrophilic property on the particle can be induced by the addition of suitable flotation reagents, such as we can use collectors or depressants, activators, or pH modifiers. It can be used in the process. So here the particles can either be naturally hydrophobic or hydrophobicity can be induced onto the particle surface by some chemical treatment. So the requirement is we need to make it hydrophobic so that it adheres to the gas bubble and it floats onto the surface of the water system, and the froth can be collected as a concentrate. So if your desired particle is not hydrophobic as inherent nature, then we have to do some chemical treatment to make it hydrophobic. Some naturally occurring hydrophobic materials, just like hydrocarbons, and non-polar solids like elemental sulfur. So these are hydrophobic in nature. I was talking about coal beneficiation process. So this coal, which is a very good example of a material that is typically and naturally hydrophobic because it is mostly composed of hydrocarbons. So when we need to do the chemical treatment to render a surface which is hydrophobic are very essential to follow a method for selective coating of the particles with monolayers of the non-polar oil. Compared to the other gravimetric processes like gravity separation or magnetic separation, flotation process is very effective and efficient to beneficiate different kind of ores, especially when the fine-grained disseminated ores are there. For from there, your valuable um, mineral should be extracted from the gangue by using the froth flotation process. Here the low-grade raw ore can also be separated into high-grade concentrate using this float flotation process. And it also solves the problem of the recovery of the useful components from fine-grained mineral particles. Thereby, for the froth flotation process, there is very high recovery rate. So we are now going to discuss about the separation of mineral particles by froth flotation process. Now you can see on the left hand side there is typical flotation process and flotation cell, but here as it is a motor induced process, so this is kind of mechanical cell. Okay, so what is happening here, that this is the water system or the pulp, and there is one motor is there. So we are introducing gas bubbles into the system, and and here you can see the more clear picture that what is happening. These green particles are hydrophobic nature. So these green particles will be attached to the gas bubbles which is sky in color, and those which are attached to the gas bubbles, those will be coming at the top, and at some point it will make a layer of this hydrophobic particle with the gas bubbles, and this layer is nothing but the froth. So this is a continuous process, suppose. So the froth which is getting generated, this will overflow and this will collected in the concentrate launder. So in the whole process, the concentrate will have our precious ore mineral, and the rest of the other impurities or other kind of ore which is not our interest, those will be hydrophilic in nature, so they will remain in the water system or in the pulp system. So over the process, this hydrophilic particle will be settled down, or those will be there inside the reactor, and those will be collected from the bottom, which is known as tailings. So this tailing will have our undesirable gangue. Okay, so this is the typical flotation process by which we are separating the mineral particles. So the next thing we are going to discuss, that is the floatability. So in the floatability, that we have discussed that it can be natural or it can be induced, or like synthetically we are making it, right? So in the natural process, those are inherently hydrophobic particles, and obviously those will be easily floatable, like paraffin, wax, graphite. Those are naturally hydrophobic in nature. So these will be collected from the skin flotation process. Whereas induced flotation, where they are having very varying hydrophobicity, those cannot be, might not be the uh, that range of hydrophobicity, but it can be modified with some chemical treatment. And the degree of floatability also depends on the type of the minerals that you are handling, and those can be collected by froth flotation process. So now we are going to discuss about the flotation process and types. So this flotation process, first one is positive flotation. So positive flotation means the foam that is floating onto the surface of the pulp, those contain useful minerals, while the gangue material or undesired material will remain in the pulp. So this is positive flotation that usually used to be occur like that. But reverse flotation means the foam that floats onto the surface of the pulp, those are not desired. Those are containing gangue material, while the useful mineral are there in the pulp. So here then it comes, if you are going for the bulk flotation and if you are going for the differential flotation process. So the bulk flotation, it floats all the useful minerals first together and then separate the useful minerals in the from the mixed concrete from the mixed concentrate individually by stages. So this flotation process is very suitable for polymetallic ore, which is useful, whose useful mineral grade is low. That is the it gangue content is very high, and the aggregation of useful minerals is closely associated with each other and has a complex structure and the fine disseminated grain size. So this from this criteria, we choose the bulk flotation for that case where the gangue content is very high. So you can see in this typical example of the bulk flotation. Suppose the raw ore is polymetallic ore. It might have more than one metal inside. So suppose this raw ore is polymetallic and it has copper, lead, zinc and sulfur. So these metals are uh, so this is the mixture raw ore. After grinding it comes, and then it is first you can see it is being flotation. By flotation, the first step, it has all the minerals, all the desired minerals are collected by mixed flotation process or bulk flotation. Then in the successive process, we are separating copper lead from the ZNS. From the copper lead, you are separating copper. So at the end, we are getting copper, lead, zinc is concentrates in a separate way. But it takes different steps to follow to separate out all the required minerals. And from each of the step, we are creating some tanks. So this is the bulk flotation process. But here what is happening? There are the collectors onto the surface of the mixed concentrate, and there are excess collectors in the pulp, which brings difficult to the next separation process. It can be seen that the problem of the reagent removal from the mixed concentrate is the key point in the flotation separation of the mixed concentrate. So these are some disadvantages of the bulk flotation. So when you are handling polymetallic ore with high grade useful minerals and coarser disseminated grain size, then we are recommending that differential flotation process should be followed for better separation than the bulk flotation process. Now coming to the differential flotation process, it separates the useful minerals to be single concentrate in a ton. It uses different reagents. These reagents make very specific mineral to float, others they sink. So this allow very high grade concentrate, and this will also reduce the amount of waste generated. So this is the typical flow sheet for differential flotation. So here the raw ore after differential flotation, this is separating out lead very specifically from the mixture, and you are getting lead concentrate. The rest of the pulp is going to the next flotation process where specifically zinc will be collecting out, and from that you are getting zinc concentrate and tailing. So differential flotation process is very effective for polymetallic ore. So now we are going to discuss about the very important topic, that is the particle and bubble contact in a flotation process. So here the flotation that we have talked about, that the particles should be hydrophobic in nature, and the flotation uh, depends on the relative adsorption or wetting of the solid surface by the fluid. In this turn, it is controlled by the surface or interfacial energy, of which the interfacial tension is the intensive factor. Now, once the particles are rendered hydrophobic, they must be brought in contact with the gas bubbles so that the bubbles can attach to the surface. If the bubbles and the surface never come in contact, then no flotation can occur. If the bubbles and the hydrophobic surfaces never come in contact, then no flotation can occur. So, contact between the particles and the bubbles can be accomplished in a flotation cell, such as it is shown here. You can see this is the typical flotation cell where air is being circulated from the middle of the sparger, and from sparger the gas bubbles are going up. So this contains the pulp, and over the time mineralized froth is collected from the top of the pulp. Here what is happening, this is the gas bubble, and minerals are attached to the gas bubbles. So the agitator, which is shown here, this one called agitator, so it draws the slurry through the stator and expel it to the sides, creating a suction that draws the air down the shaft of the stator. The air is then dispersed as the bubble throughout the slurry, and the bubbles are coming in contact with the particle in the slurry that is drawn through the stator. So here the particle bubble collision is affected by the relative sizes of the particles. If the bubbles are larger relatively from the particle, then the fluid flowing through the bubbles can easily sweep the particles past without coming in contact. It is therefore best if the bubble diameter is comparable to the particle diameter in order to ensure good particle bubble contact or good bubble adsorb onto the particle. So it should not be there that the gas flow rate is so high that the gas doesn't take that much of residence time, or it just flows the particles out of the system. So this kind of higher gas flow rate will affect the separation. So we need to maintain the air flow rate and also the bubble size, so that the bubble size are comparable um, with the grinded particles, solid particles, so that there is good contact between the bubble and solid. So this particle bubble interactions is it depends on the contact between the air bubble and the solid particle, which is governed by different forces acting on the mineral surface and the air bubble in the aqueous medium. So here you can see the picture where contact angle between the air bubble and the mineral surface in a water system has been shown. So this is typical solid mineral surface and this one is gas bubble. So this one is water system outside. So here it makes a at this point of contact, if you are making the tangent, if you are doing the analyzing the forces acting on this point of contact, then you will be calculating the contact angle. The ability of the mineral particles to displace water and to attach to the air bubble can be described by the contact angle. So this is what the definition of the contact angle. Now minimizing the Gibbs free energy of the bubble surface system at equilibrium that yields the Young equation relating the three interfacial energies and the contact angle. By so at equilibrium, so at equilibrium, okay, we get that MA will be equals to WM plus WA cos theta. So from here, cos theta will be so where theta is the contact angle, MA is the surface energy between material and air. WM is the surface energy between solid and water. WA, it is the surface energy between water and air. So if the contact angle theta approaches to 0, then the mineral air contact is replaced by the mineral water contact, and there will be, if there is mineral water contact, then there is no flotation because it becomes hydrophilic. The mineral becomes hydrophilic. For flotation to occur, a mineral air interface must be created with simultaneous destruction of the air water or mineral water interfaces of equal area. Thus, for bubble mineral particle attachment to take place efficiently, the contact angle must be finite. And this force balance, this mineral air and water mineral, this difference should be lesser than water air uh, surface energy. Now, the bubble particle interaction is often described in terms of change of free energy, which is also known as work of adhesion. So, this work of adhesion is the work which is equal to it is the work required to separate the solid air interface and produces separate air water solid water interfaces. So this is the work of adhesion, which is termed as they produce the solid air interface and separate the air water and solid water interfaces. So it can be seen that the greater the contact angle, the greater is the work of adhesion between the particle and the bubble. And they will be more resilient the system So this is how the work of adhesion is defined. So in the flotation process, a solid particle is attached to the bubble in the same way as the solid and bubble are in contact in the shown figure. Only the difference is that the solid is extremely small and the air bubble is extremely large. So the force of gravity and the agitation tend to dislodge the solid particles from the bubble. If the contact angle is very small, liquid will advance over the surface of the solid and the surface forces holding the solid and bubble together will be very weak. If the large contact angle, that means there will be easy floatability. So when the solid particle attaches itself to a bubble, there is loss of surface energy per unit area of the surface. That is equal to the loss in the surface tension. This loss in energy is measured by the wettability of the solid phase by the air, and therefore it is an indication of the floatability. It presents the work required to separate the air from the unit surface of the solid. So, suppose you are I am redrawing the concept, that is, this is the solid surface and this is the point of contact. Making an angle theta. So this is the solid liquid surface. This one is the gas phase. So this is the gas liquid uh, interface. And this one is complete solid, right? So here the surface energy will be noted as This is the surface. And we also know that so this equation becomes, so this is when the surface energy is defined in terms of the contact angle and the unit surface area. So we are going to discuss about the floating reagents. So floating reagents are used to modify the surface property of the minerals to make it more suitable for flotation process. So here you can see that numerous inorganic and organic reagents, surfactants are employed in a flotation process for controlling the characteristics of the interfaces. According to their functionality, flotation reagents are classified into collector, regulators, and frothers. So first we are going to discuss about the collectors. What are the collectors? So these flotation reagents preferably adsorbed onto the solid-liquid interface, making the surface of the wanted mineral water repellent or hydrophobic and facilitating the bubble particle attachment. So these collectors are classified based on the composition, whether they exist as cation, anion, or molecular species in water. Therefore, collector molecules may be ionizing compounds which dissociate into ions in water, or it can be non-ionizing or non-polar compounds which are practically insoluble. The rendered mineral water repellent or make them hydrophobic by covering its surface with a thin film. Ionizing collectors have a very complex asymmetric molecular structure which comprises functional polar head group and a non-polar hydrocarbon chain. You can see this kind of polar collector interaction with solid and water interface. Here the non-polar tails are into the water system, and by the polar head it is connected to the solid. Thus this non-polar hydrocarbon chain, they make it hydrophobic. So by this process of introducing collectors, if they are making the mineral surface hydrophobic, then they will enhance the flotation process. So this one is typical industrial flotation collectors. Here the R groups are represented by different hydrocarbon chains and hydrogen atoms in the cationic collectors. So collectors can be divided into ionizing and ionizing group. Non-ionizing, they are liquid non-polar hydrocarbons which do not dissociate in the water. Whereas ionizing, they are anionic or cationic or amphoteric collectors. So anionic collectors are oxyhydryl based upon the organic and sulfur acid groups. There can be carboxylic or fatty acid and soaps. They can be also used as a collector. Sulfates can be used as a collector and sulfonates can be used also as a collector. Here the R groups are different hydrocarbon chains. Whereas sulfi, uh, sulfihydryl, this can be bivalent sulfur, xanthalate or dithiophosphates. This can be used also as a collector. For cationic is water repellent or hydrophobic based on the pentavalent nitrogen. These are the various collectors industrially used for improving the flotation process. So now we are going to discuss that what are the non-ionizing collector. So this we have already seen the examples of the non-ionizing collectors. So these collectors do not contain any polar functional group and they cannot chemically be absorbed onto the mineral surface. So these compounds are hydrocarbon liquids of the petroleum origin and they adsorbed onto the surface of the mineral due to the intermolecular van der Waals forces, not chemically. So these collectors are primarily used in the flotation process of naturally hydrophobic mineral such as coal, graphite, sulfur, molybdenite, which has insufficient hydrophobicity in nature naturally. For the strong and fastest attachment of the bubble, we introduced non-ionizing collectors. They are also used in the combination with heteropolar collectors for coarser particle flotation of copper sulfides or phosphate minerals to reduce the consumption of the xanthalate and fatty acid and to strengthen the bubble solid attachment. Whereas ionizing collectors, so these collectors are widely used in the flotation and can be conveniently divided into two classes. First one is the thio collectors, which are represented by alkyl xanthates, dithiocarbamates, thionocarbamates, mercaptobenzothiazole. These are some thiocollectors. The non-polar tails of this collector are relatively short alkyl hydrocarbon chain or occasionally cyclic hydrocarbon ring like phenyl or cyclohexyl these are used. Non-thio collectors represent alkyl carboxylates, alkyl sulfates, amines, and substitute amines. The alkyl chains of these collectors usually change from lauryl to octadecyl or olein. The most important properties of the thio and non-thio collectors in aqueous solution include solubility, oxidation, and micellization. So these micelles form because of the hydrocarbon chain is non-ionic in nature and a mutual incompatibility between the polar water molecules and the non-polar hydrocarbon chain exists. So when a certain concentration of the surfactant ions is reached in the solution, termed the critical micelle concentration or CMC. The hydrocarbon chains associated into aggregates or micelles they form and come out of the solution. So the CMC of the flotation collector is of the order 1 millimole per liter. These micelles cannot be seen by open eye like bare eyes, but their presence can be noted by ability to scatter light when the beam is passed through the solution. So this micellization assumes an important role in the flotation process. If the concentration of the collector used added in the solution exceeds this CMC value, micellization occurs and the concentration of the collector available for the mineral adsorption is greatly reduced. So there are some important characteristics of the ionizing collectors when it is in the solution. In category of thiocollectors, they are highly soluble in water, do not form any micelles in water, and highly susceptible to oxidation, do not significantly decrease the surface tension of their solution. And they readily react with heavy metal ions, producing hydrophobic precipitation on the mineral surface. Whereas non-thiocollectors, they are less soluble in water, they form the micelles in water, have no susceptibility to the oxidation, and is stable with time and temperature, can significantly decrease the surface tension of the solution. Carboxylates have very high affinity toward the metal ions, giving very hydrophobic precipitation onto the surface, similar to thiocollectors. Other non-thiocollectors do not readily react with the inorganic ions. So now we are going to discuss about the regulator after the collector discussion. So regulator, a number of the inorganic reagents, those are used to control the flotation by regulating the solution chemistry. So these regulators can be activator or can be depressants or can be dispersant or pH modifiers. Activators can alter the chemical species of at the mineral surface, which enhances the collector adsorption. The activators are generally soluble salts. Example, flotation activator include copper or lead sulfates used to increase the floatability of the sphalerite, and sodium sulfide or hydrosulfide used to create sulfide component onto the surface of the oxide minerals, which can be floated easily by the xanthates. Whereas depressants are used to increase the selectivity of the flotation by rendering certain minerals hydrophilic, thus preventing them to float. Thus they depress the floating characteristics of that mineral and preventing them by floating. Cyanides and polymers are the best example as depressants used in the flotation process. Cyanides can dissolve and remove stable xanthate salts from the surface of the sulfide minerals. Polymers can adsorb onto the hydrophobic surface, making them very hydrophilic. Here the pH modifiers play a very important role, though very complex, role in flotation and specifically in selectivity of the complex ore separation, which is dependent on a delicate balance between the reagent concentrations and pH. So this flotation is often carried out in an alkaline medium since most of the collectors including xanthates are stable under these conditions and corrosion of cells and pipes is minimized. Alkalinity is controlled by lime and sodium carbonate. Sulfuric acid or sulfurous acid can be used when a decrease in pH is required. So these all are the criteria of regulators. Now we are coming to the part of frother. Frother. So frothers are reagents which are water soluble organic reagents that preferentially adsorb onto the gas liquid interface, helping the production of small bubbles and a transient stable froth. So these are heteropolar molecules with a polar group to provide solubility in the water and a nonpolar hydrocarbon group for the adsorption. Frother are very similar to the ionic collector in many aspects, and to the extent that many collectors such as oilettes are also very powerful frothers. These powerful frothers produce very stable froths which cannot allow efficient transport of the flotation products to further processing. So froth buildups on the surfaces of thickeners and excessive frothing of the flotation cells can be problematic at many mineral processing plants. A good frother should have negligible collecting power and should produce a transient stable froth required for transporting the floated minerals to the concentrate launder. So the most effective polar groups for frother introducing include hydroxyl group, carboxyl group, carbonyl group, amine, sulfur. So these are some good frother groups. Alcohols and related compounds like glycol ethers are most widely used frothers. They can largely be because of their inability to adsorb onto the mineral surface. Aromatic alcohols from the natural sources, such as pine oil, have been used extensively. Synthetic frother are now widely used and have the controlled composition, which assists in maintaining the plant stability. Now, methyl isobutyl carbinol and the polypropyl glycol ether are in this category under various commercial names. Frothers based on polyglycols are also commonly used in various blends with alcohol and polyglycol ethers, which provide special frother for flotation circuits. The alcohol groups provide a selective but often brittle froth which allows good control and product transportation. The glycol ether are stronger than the alcohol groups. Now the polyglycols are the strongest frother considered in flotation. Non-alcohol frothers include acids and amines. The carboxylic acid are also very powerful collectors, but collecting and frothing properties in one reagent may reduce the flotation selectivity. Frothers with amine and sulfur group also have weak collector properties. Surface inactive frother include few special reagents such as diacetone alcohol, ethyl acetal, which behave like frother in the solid liquid air system but not in two-phase system like liquid air system. So here the molecules of these reagents have two polar groups and are readily soluble in water. They adsorb onto the solid surface but do not significantly change their hydrophobicity. During the bubble particle interaction in the froth phase, the adsorbed molecules of the surface inactive frother can change their molecular orientation and produce a sufficiently stable three-phase froth. The surface inactive reagents do not reduce the surface tension, and they maintain the magnitude of the capillary forces needed for strong bubble particle attachment in flotation. So these are some typical flotation frother: polypropyl propylene glycol ether, MIBC, that is methyl isobutyl carbinol, terpenol, xylenol. These are some flotation frother commonly used. Now we want to know that the factors affecting the flotation. Liberation. Liberation of the valuable mineral from the gangue material is carried out by comminution. Successful flotation process necessitates correct degree of liberation, and well liberated particles will enhance the action of the reagents that we are adding to the surface of the mineral. Also the particle size. So the particle size mainly determines the degree of liberation and the lifting power of the bubbles. Most of the minerals, except coal, are subjected to fine grinding ranging from 100 to 75 micron size fractions. The recovery and the selectivity index of the value mineral decreases with the increase in size. And the last important factor is the pulp density. Effective flotation process is carried out in higher pulp density. However, the pulp density in the mineral flotation varies from 25 to 45% by weight, and it may be as low as 10 to 8 to 10% in a coal flotation. Now we are going to discuss about the flotation circuit. So this is typical the flotation circuit. Here the feed is introduced first for the grinding, and then after grinding the liberation occurs where the valuable mineral particles from the gangue material, those are being liberated, and this liberation ensures that the valuable mineral are available for the attachment to the air bubbles in the flotation process. Grinding usually takes place in ball mill or rod mill until the desired particle size is obtained. Then it goes to the rougher flotation. The rougher flotation cells perform the initial separation of the valuable minerals from the most of the waste mineral, and the ground slurry or the pulp is mixed with some reagent, that is collector or frother or modifiers, where the air is introduced into the flotation cell, creating the bubbles to attach to the hydrophobic mineral particles, and the froth phase which is rich in valuable minerals overflows from the rougher concentrate to the scavenger cell, and the remaining rougher tailings goes to the rougher tailings goes to the froth phase overflows as the rougher concentrate, and while the remaining slurry is sent as the rougher tailings to the scavenger stage. So in the scavenger flotation, which helps to recover additional valuable mineral, those are not was able to flotate in the rougher stage, and the scavenger flotation cells treat the rougher tailings more efficiently. The scavenger concentrate is recycled back to the regrinding circuit for cleaning circuit, and the remaining material after scavenger flotation becomes final tailing, which contains minimal valuable minerals. Now what happens that regrinding mill here, it helps to grind the rougher or scavenger concentrate and liberate any remaining residual mineral particles, and the regrinding step will help to reduce the particle size, improving the liberation and ensuring the higher purity in the subsequent cleaning stages. So the reground slurry is then sent to the cleaning stage for upgrading. So cleaner flotation, that is cleaner one stage, that is to upgrade the concentrate by removing the remaining gangue minerals. The regrounding concentrate passes through multiple cleaner stages, which each cleaner flotation produces a purer concentrate with high grade and sends its tailing either back to the previous state or it goes to the regrinding circuit. Whereas cleaner 2, it produces the final concentrate which is rich in valuable mineral and ready for the further processing, which is for smelting. So this final concentrate that we are getting here, it is high grade product containing most of the valuable minerals being separated, and the final tailing is the considered to be the waste stream with very low residual valuable mineral, and these are usually sent to the tailing pond, and there will be clear water in each step. Those will be recycled for the milling purpose or in the flotation unit. So the last section that we are going to discuss in today's class, that is the flotation cell. So there are basically two kinds of flotation cell. One is mechanically driven flotation cell, and one is pneumatically driven flotation cell. So here you can see this is one a mechanical flotation cell. So It is equipped with a stator and a rotor to keep mineral particle in the suspension and disperse the air supplied through the central pipe, and it bubbles up. Because of the more violent agitation, they may give more thorough flotation, and the tailings nearly free from the material desired in the concentrate. But the concentrate then contain more gangue than those from the cells with less agitation. So high altitudes auxiliary air under moderate pressure is frequently supplied to the mechanical cells. So these mechanical cells have a greater capacity for the same volume and also help conditions the pulp and having greater capacity to the conditioner. Next one is pneumatic uh, flotation cell. Here you can see the air aerators are pressed, which high pressure air is being bubbled up. There is no mechanical rotor, and here uh, pneumatic cells are typically classified as very high intensity flotation mechanisms with rapid kinetics, resulting in shorter residence times and often half that of mechanical flotation cells and a quarter that of flotation column. It depends upon compressed air for agitation it is being used and give a relatively mild agitation and produce a cleaner froth relatively free. About 50% longer contact time is being provided in the pneumatic machines, and pulp must be fully conditioned before flotation. So we have discussed about the flotation process, and in the industry also for the different ore beneficiation process, this flotation process is very important, and uh, I will share this lecture by very soon, maybe by tomorrow. And that's it. All the chapters and the course content we have discussed and completed today. So, best of luck for your upcoming exam for mechanical unit operation. Hope you will do good. And if there is any query and any doubt regarding the any kind of numerical that you want to discuss before your exam, that you can drop me a message, or you can put the question in the question and answer platform of NPTEL platform, that NPTEL online site. So that's it. I will like to end to this class, and hopefully we will meet in another subject. Thank you.